Welcome to this explainer. Today we are going to unravel the totally invisible physics and, honestly, the fascinating history behind how colossal steel structures, which are literally veritable floating cities, defy what seems like basic logic just to stay afloat. We're going to explore the ancient math that makes this possible, and the incredibly ingenious modern engineering that keeps these absolute behemoths upright and stable even in the most turbulent oceans.
Okay, let's dive right into this. Imagine standing on a beach. If you pick up a tiny 1-ounce pebble and toss it into the ocean, what happens? Right, it sinks instantly. It's incredibly dense for its size, and gravity pulls it straight down to the bottom without a moment's hesitation. But right now, all over the world, there are 200,000-ton steel cruise ships. We're talking vessels carrying thousands of passengers, multiple swimming pools, ice rinks, the whole shebang, floating beautifully on the surface of that exact same water. So you have to ask yourself, how on earth does a skyscraper made of thick, heavy steel manage to float effortlessly while a tiny pebble drops like a stone?
To truly understand this paradox, it helps to look back at history. For thousands of years, humans naturally built ships out of wood. It made perfect sense. Throw a log into a river, it bobs on the surface. Wood just has a natural buoyancy to it. But in the 19th century, the Industrial Revolution completely changed the demands of global trade. Engineers wanted vastly bigger, stronger ships powered by steam, and that meant using iron and steel. Up until then, metal was strictly used for small components, nails, fittings, never for an entire hull. So in 1843, when a visionary engineer named Isambard Kingdom Brunel built the massive iron ship the SS Great Britain, the public genuinely thought he was out of his mind. The common belief at the time was literal and blunt. Wood floats, iron sinks. It is common sense. Crowds actually gathered at the launch, watching in utter suspense, fully expecting this metal beast to plunge directly to the bottom of the sea. But no way, it didn't.
Now, Brunel wasn't defying physics here. He was relying on a fundamental law of nature discovered over 2,000 years earlier in ancient Greece. A brilliant mathematician named Archimedes actually unlocked the secret to the structural engineering marvel. He stated this exact principle. Any object, wholly or partially immersed in a fluid, is buoyed up by a force equal to the weight of the fluid displaced by the object. That simple, profound sentence that is absolutely crucial. It's the absolute key to everything we're talking about today.
Let's break that down by looking at the core concept of displacement. Legend has it that Archimedes was stepping into his bathtub when he noticed the water level rising over the edges. He realized his physical body was actually pushing the water out of the way. The volume of water that spills out or rises up directly corresponds to the volume of the object submerged. Upon this realization, he famously shouted, "Eureka! I have found it!" And you know what? This is exactly what our 200,000-ton cruise ship is doing. As the ship settles into the ocean, it pushes a massive volume of seawater out of the way. It's literally the bathtub experiment, just happening on a macroscopic, monumental scale.
But here's the thing. Displacement is only half the story. The other half is buoyancy. When an object pushes water out of the way, the water doesn't just sit there, it actively fights back. This happens because fluid pressure naturally increases with depth. The deeper you go, the heavier the water pressing down from above becomes. And this creates a relentless upward pressure on the bottom of whatever is submerged. If the object weighs more than the water it pushes away, that upward push just isn't enough, and it sinks, like our pebble. But if the object weighs less than the displaced water, the upward fluid pressure successfully holds it up.
So, the crucial point is this delicate balancing act. Picture a constant and visible tug-of-war happening beneath the waves every single second a ship is out on the water. On one side, you have gravity constantly pulling downward. That's a force determined by the combined mass of the ship, the cargo, and every single passenger inside it. At the exact same time, you have the water pressure aggressively pushing upward. This upward buoyant force must counter the downward gravitational force perfectly. When these two opposing forces equalize, the object achieves a state of equilibrium. The tug-of-war ends in a tie and the ship floats. But wait. Actually, let's think about this. Steel is incredibly heavy. How on earth does a massive steel ship displace enough water to float without sinking first?
Well, this brings us to the real engineering secret: empty space and volumetric density. If you drop a solid, dense block of steel into the water, it absolutely sinks, for sure. The steel itself is far too dense, but a ship isn't a solid block of metal. The hull is shaped like a giant, wide bowl. Inside that heavy steel shell are cabins, vast corridors, sprawling engine rooms, and predominantly trapped air. And air is incredibly light. To find the average density of an object, you divide its total mass by its total volume. When you take the heavy steel of the hull and combine it with the massive volume of trapped air inside, the average density of the entire ship becomes significantly less than the density of the surrounding water. Because the ship's hull is built so remarkably wide and deep, it pushes a colossal amount of water out of the way, generating a massive upward buoyant force easily capable of carrying its weight.
Now, what's really interesting about this is how naval architects actually map this out to keep a ship upright. If we look at a vessel resting in still water, there are two critical points. The center of gravity, marked with a G, represents the exact focal point of the downward thrust of the ship's entire weight. Below it is the center of buoyancy, marked with a B, representing the focal point of the upward push of the displaced water. When a ship is floating perfectly upright in a state of equilibrium, G and B are perfectly aligned on the exact same vertical line, pointing straight up from the bottommost part of the ship, which is known as the keel or K.
But the ocean is rarely perfectly still. What happens when a strong gust of wind or a heavy wave hits the side of the vessel? The ship tilts, or in nautical terms, it heels over. As the vessel heels, a wedge-shaped section of the hull is lifted out of the water on one side, while the brand new wedge is submerged on the opposite side. Because the physical underwater shape of the ship has now fundamentally changed, the center of the displaced water changes too. The center of buoyancy actually moves. You can map it shifting outboard to a new position B1. So if the downward pull of gravity remains static in the center, but the upward push of buoyancy moves to the side, what happens to the ship? Well, this shifting center of buoyancy introduces arguably the most critical term in naval architecture, the metacenter, or M. Imagine drawing a straight vertical line straight up from our new shifted center of buoyancy, B1. The exact point where that upward line intersects the ship's original center axis is the metacenter. Think of it as a theoretical pivot point just suspended in the air above the ship. For a vessel to have what engineers call positive initial stability, meaning it naturally possesses a righting arm that will force it to snap back to an upright, safe position, this metacenter, M, absolutely must sit above the center of gravity, G. As long as M is higher than G, the physics of the water will always fight to push the ship back upright. And this brilliantly illustrates exactly how that righting mechanism works. It's highly intuitive if you visualize a simple baby's rocking cradle. The cradle itself represents the ship, and its center of gravity is located right near the middle. The curved wooden rocker touching the floor represents the center of buoyancy. As you push the cradle over to one side, the physical point where the rocker touches the floor shifts outward. That outward shift provides the mechanical leverage needed to push the cradle back upright the second you let go. A heeling ship's shifting buoyancy acts exactly like that curved rocker on the floor, providing the constant leverage needed to stay upright.
The actual physical distance between the center of gravity and the metacenter is known as the metacentric height. And this specific measurement dictates the personality of a ship, how it handles and reacts to the waves. If you have a large distance between G and M, you have what naval architects call a stiff vessel. It will fight heels aggressively and roll back to an upright position very quickly, and sometimes violently. On the flip side, if the center of gravity is too high, bringing it dangerously close to the metacenter, you get a tender vessel. It leans over easily and takes a long, sluggish, and precarious time to return upright. Interestingly enough, massive cruise ships are deliberately engineered to be slightly tender. A stiff ship would snap back so aggressively that passengers would be thrown around, spilling their coffee everywhere. A tender design ensures a slow, comfortable, sweeping roll that is much gentler on everyone aboard.
Let's move to real-world safety limits and see how this builds. Consider a commercial fishing vessel. If you load a massive, heavy catch of fish high up on the main deck, the ship's center of gravity, G, is pulled upward, dragging it much closer to the metacenter, M. This drastically decreases the metacentric height, meaning the ship becomes incredibly tender. If a large, unexpected wave hits the hull now, the righting force is so weak that the ship is at a severe and immediate risk of simply rolling over and capsizing entirely. This is exactly why heavy weights, cargo, and engines must always be stored as low as possible in the hull. You gotta keep G's safely anchored at the bottom. Actually, this dynamic gets even more dangerous with suspended weights. If a ship attempts to lift a massive, heavy net of fish out of the water using a crane or boom, physics dictate something terrifying. The center of gravity of that heavy net acts upon the ship not from where the net is literally hanging, but from the very top point of suspension, the tip of the boom, high in the air. Not only does this instantly shoot the ship's overall center of gravity dangerously high, but if the boom suddenly swings to the side, it dynamically multiplies that heeling force.
A sudden uncontrolled swing exerts a massive, violent torque that can effortlessly flip even a sizable vessel in a matter of seconds.
Because adding too much cargo inevitably sinks a ship deeper into the water and drastically changes its average density, overloading became a massive, deadly problem during the industrial boom. Ships were literally sinking mid-voyage because they lost their critical pocket of trapped air. Thousands of sailors lost their lives to what became known as coffin ships, vessels intentionally overloaded by greedy owners who valued cargo over human life. To put an end to this tragedy, in the 1870s, a British politician named Samuel Plimsoll introduced a brilliant, mathematically simple lifesaver. He successfully mandated that a circle with a horizontal line through it be painted on the outer side of every commercial hull. This became known as the Plimsoll line. It acts as an absolute, non-negotiable visual limit. As long as the ocean water doesn't rise above that painted line, the ship's displacement and average density remain mathematically safe for travel. A real game changer.
When you finally see the invisible forces at play, the sheer scale of maritime engineering becomes profoundly awe-inspiring. A colossal steel ship is not defying gravity. It is executing a flawless, continuous masterclass in structural geometry. It requires perfectly balancing trapped air, precisely calculating metacentric height, and leveraging Archimedes' 2,000-year-old math to basically borrow the immense strength of the ocean itself. So, I leave you with this thought. The next time you see a colossal 200,000-ton steel city gliding effortlessly across the horizon, knowing the delicate mathematical tug-of-war silently keeping it upright and afloat, will you ever look at it the exact same way again? Thanks for joining me on this explainer, and stay curious.